Hello, I'm Ron Litchford, Principal Technologist for Propulsion. Over the past several months, NASA's Space Technology Mission Directorate has worked to establish a strategic framework setting out our future vision within the context of four thematic thrusts: go, land, live, and explore. My purpose today is to provide you with a brief introduction to the Advanced Propulsion and Vision Future Priority Strategy, which resides within the GO thrust alongside cryogenic fluid management and nuclear propulsion focus areas. We're very pleased to share this vision and seek your valuable insights and feedback as we embark in partnership on an inspiring path of science, exploration, and commercialization. To set the scope of our advanced propulsion technology vision, it is first useful to characterize the architectural underpinnings of our expansive spaceflight aspirations. This is a graphical depiction of those ambitions, serving the four intertwined goals encompassing science, exploration, commerce, and security. Note that these high-level goals are categorized into three distinct destinational regimes. In the near term, our focus is on establishing the technological foundations that will fully enable a LEO to cislunar development path, resulting in commercially sustained enduring infrastructure. From a transportation perspective, these nearby operations can be accomplished with conventional chemical and solar electric propulsion solutions. As we push further out into the meso-solar regime, however, including fast-crewed Mars missions, consideration of nuclear propulsion solution becomes essential. Thus, we are naturally led to a littoral and blue water mobility analog with strong similarities to a naval transportation architecture. As we push out even further toward our highest aspirations in the very distant extrasolar domain, we encounter distance and time scales so challenging, so enormous that advanced energetic propulsion processes and concepts become a compelling research and development objective. Altogether, this expansive collection of spaceflight goals provide the contextual backdrop for our advanced propulsion technology vision. Now, with this backdrop in mind, we're now positioned to consider the foundational basis of our advanced propulsion and vision future, as summarized in this graphical depiction. Note, first of all, that this vision consists of two distinct focus categories. There's the architecture-driven propulsion technologies category aimed at established architectural capability needs, and inspiration-driven research category aimed at new transformational capabilities that would completely revolutionize our means of space transportation. Now, within the architectural-driven category, the technology objectives include a multitude of high delta V electric propulsion capabilities at increased power range. There's also high delta V sub-kilowatt electric propulsion capability for ESPA-class spacecraft. Greater adoption and infusion of green propellant propulsion. Development, qualification, and flight of code-tolerant storable propulsion based on high-mod bipropellant combinations. Unique observational platforms derived from propellantless solar cell capabilities. And more able robotic science spacecraft based on low to moderate power nuclear electric propulsion. Our transformational capability research category, on the other hand, is very much oriented at sustained research investments that can enable the possibility for new breakthrough technologies. Here we intend to pursue a wide range of advanced energetic propulsion processes and concepts that can potentially meet our highest aspirational capability goals. The technology outcomes captured within our advanced propulsion and vision future are indexed and organized here as feeders into three distinct technology development streams. The exploration-aligned development stream, for instance, includes gateway, PPE, solar electric propulsion, cryogenic propulsion, and nuclear propulsion as exploration system enabling technologies supporting moon to Mars architectures. A second development stream encompasses those propulsion technologies aimed at overlapping science, commerce, and security mission applications. The third development stream are transformational capability R&D priorities. Of those transformational capability R&D priorities include rotating detonation rocket engines, low to moderate power nuclear electric propulsion for robotic spacecraft, near-sun solar thermal propulsion to enable solar perihelion burn oberth maneuvers and the attainment of high solar system escape velocities, and fusion and other advanced energetic propulsion technologies for fast and efficient solar system-wide access. Note that these technology development streams are all designed to pursue both near and far-term goals with a variety of in-state TRL objectives. As a basis for understanding gaps in development needs, we now consider the technological state-of-the-art, and we'll begin with electric propulsion systems. This table summarizes our assessment of current electric propulsion system capability with respect to mission, application needs, and system power classes. Note that this assessment organizes the state of the technology into three general categories: flight system available, number one; number two, development underway to meet application requirements; and number three, significant development required. Also note that our indexed technology capability objectives are overlaid on this assessment to provide a direct mapping to current development status. Some key supporting project and program efforts are also indicated for reference. This table summarizes our assessment of current chemical propulsion capability with respect to mission application needs and thermal propulsion type classification. Now again, this assessment organizes the state of the technology into three general categories: one, flight system available; two, development underway to meet application requirements; and three, significant development required. So in a similar fashion, our index technology capability objectives are overlaid on this assessment to provide a direct mapping to current development status, and some key supporting projects and program efforts are also indicated for reference. Our final state-of-the-art assessment encompasses space nuclear power systems supporting nuclear electric propulsion applications. Because system-specific mass or specific power represents the single most important gauge of nuclear propulsion capability, we provide a plot of this parameter for various system types with respect to total power. Now, the state of the technology is here organized into three broadly defined groups: flown, studied, or notional. The general mission application agreements are also indicated by the dash-bounded regions. So in a similar fashion as before, our index technology capability objectives are overlaid on this assessment to provide a direct mapping to current development status, and some key supporting project and program efforts are also indicated for reference. In conclusion, we present a high-level development strategy that defines our each desired architectural outcome and its corresponding technology capability goal. Recommended programmatic actions for attaining each objective are briefly described, along with the anticipated investment trend. Generally speaking, our architectural-driven propulsion technology strategy is essentially on track to achieve the desired end goals. The emphasis now is on sustaining portfolio commitment and execution to delivery, with some ramp-up investments in a few key areas. Our transformational R&D portfolio, on the other hand, has been a long-standing underserved investment priority and is in need of significant programmatic restructuring and investment augmentation. It's our fervent hope to revitalize this segment to the extent possible under stringent budgeting constraints. In closing, I refer you to the propulsion technology taxonomy domain utilized throughout this envisioned future priorities discussion, as well as a complete glossary of referenced acronyms. We sincerely appreciate your attention, consideration of our future vision for space technology. More so, we very much seek your feedback and suggestions as we strive to make this a shared and equitable vision of inspired space exploration for the entire community. Thank you.